I could not post any videos for the last 3, 4 days. Maybe you noticed that there's this viral fever going on in Calcutta. Anyway, so today we will do a very nice problem. This is from one of the problem solving sessions at Chinda, the mathematical Olympiad related problem solving sessions. And this problem is actually from American math competition. It's a very beautiful problem. And when I first looked at the problem, I actually did not understand the statement very well. And then one of the students at Chinda, Tanish, I think, he came forward and said that, okay, that maybe the problem is trying to say this. So then he told me how he would solve it, and it was very beautiful. I thought I would share it with all of you. All right. So let's solve this problem together, and we will learn something new today. And I'll also ask a question in between, as usual. And we are still giving awards out for the best commenter. So if you think that you know the answer to those questions, please put them in the comment section. All right. So the idea is very simple, actually. You take a rectangular prism like this. So here we go. And the side lengths of the rectangular prism are also given. So it's like 1, 2, and 3. I don't know the exact numbers in the actual American math competition paper, but let's make up some numbers now. 1, 2, and 3, suppose. Now, what the problem defines, and this is very interesting, it actually talks about the neighborhood of this prism. So it doesn't use the word neighborhood. So that's why I was taken a little bit by surprise, because it defines the neighborhood. So the way it says it is this, that take all points r distance away from some point on the prism. So this is precisely what our neighborhood of a particular set is. You take everything that is r distance away from a certain set of points. Okay, so I'll give you an example. So let's say if you have only one set of points at most, let's use the word at most. Okay, so if you have just one point and you want to take all the points which are at most r distance away from this one point, then what you do is you take the disk, which is of radius r. So that is the collection of all points which are at most r distance away from this pink point. Okay, so this is you just start with one point and you get a disk around it. This is the r neighborhood, the closed r neighborhood of a singleton point. Okay, what if you don't have just one point? What if you have like 2 points? Let's say if you have 2 points. So let's draw that. Suppose you have 2 points. Then what do you do? Well, it's very simple. You take the R neighborhood of the first point. Maybe it's like this. The R neighborhood of the second point. Maybe it's like this. And you take the union of them. So the entire region, the entire shaded region is now the R neighborhood of this pair of points, the 2 points. I'll give you one more example. Suppose instead of having two discrete points, you have just a segment like this. What is the R neighborhood of this segment? Well, again, it's quite simple. What you do is you take every point on this segment, draw a R disk around it. R is the radius of the disk, by the way. Now take another point. So you do this for every point actually. You draw the R disk around it. You draw the R disk around it. So like this, you keep on drawing R disks. There will be a lot of overlaps, of course. There will be a lot of overlaps. But finally, you'll get tube-like, this tube-like object. So you can easily imagine that this will be like this, right? It would look somewhat like this. So maybe I just so everything here. So you just shade all of that. This is the R. It's sometimes known as the tubular neighborhood because it looks like a tube. The tubular neighborhood. Now we do this for a single segment, a one-dimensional strip. Now you could do this for this prism as well. It's a three-dimensional object. So what you do is at every point you put in a sphere because you're working in three-dimensional space. So now your R disk, all the points which are at most R distance away from a single point, is a disk. It's not a disk, it's a sphere, right? It's a sphere, it's a solid sphere with the interior, right? So you do this for every point and it will sort of become like a like a coating, like a cloud over the entire prism. So it will be like a packaging of the prism. You can think of it like that, right? It's like a packaging of the prism. So the main question is, what is the volume of that packaging and the prism? So you just, I mean, they actually phrased it a little bit differently because they wanted to do a multiple choice question, but that is the main content of the question, that if you do this, what is the volume? The question is, what is the volume of this R neighborhood of the prism? Okay, so Tanish immediately recognized that this is the meaning of the question, and then we all started solving it. In fact, he proposed the solution. It's not very hard actually, it's quite simple. So let me tell you a little bit more about it. So if you look at this problem, it's a solid prism. So if you take the point here, let's take a point on the surface of the prism, and if you draw a sphere, right, like this, around this point of our neighborhood, part of the sphere will sort of be inside the prism, right? It will be inside the prism. So you don't really have to calculate that part. You have to just take the volume of the prism and all the parts which are sort of inside the prism, the volume of the prism will eat all of them away. So you don't have to even worry about that. So you only have to worry about the parts which are jutting out, which are outside, right? Okay, so how do you do that? How do you calculate that? Well, different things are happening at different portions of the prism. So let's look at each of them one by one. So what is happening on this surface? What is happening on this surface? Well, clearly something like this. So from every point, I have to go R unit in one direction, right? R unit in one direction. And it's definitely, okay, maybe I can just take this entire thing, make a copy of it, and place it somewhere here. Okay. All right. So what I have to do is from every point, I have to go R unit outward, because inward, it's just the solid prism. I actually go inward as well, but it's just a solid prism. And I will calculate the volume of the prism separately. It's just 1 times 2 times 3. It's not hard. Volume of prism, or this, sometimes we call this a rectangular parallelepiped, is just 1 times 2 times 3, which is length times width times height, which is 6. So stuff that is going inside, we don't worry about that too much. Let's look at the stuff that is coming outside. So it will all come outside by R units. From every point, it will come outside. So we will have something like this, a thick layer, a thick layer that is jutting out of the prism, like coming out of the wall. And the same thing will happen here. So the better you draw, the better you will understand what's going on. And in fact, for each of the 6 walls or 6 faces, the same thing will happen. So what are the volumes of these pieces that are sort of jutting out, coming out? Well, for example, for this one, it will be 1 times 2 times R, right? Length times height times width. So it's 1 times 2 times R plus this one will be 2 times 3 times R, 2 times 3 times R, and then there will be one at the top, so it would be somewhat like this. So let's put it up like that. Forget this piece for the moment. Let's put it up like this. So you have one at the top. I mean, I'm not saying that there are no other pieces. I'm just calculating them one by one. So one that is pushing up at the top, this one is 1 times 3 times R. 1 times 3 times R. And we have to double all of that because, well, you notice that for this face, there is one at the back as well, right? So there are pairs. So there are 6 of them. So for each, we have one on the other side. So this is the entire volume of the pieces that are sort of coming out of the walls or the faces. Okay, so that one portion is done. So this is 2R plus 6R plus 3R. So that's 22R in total, right? If you just multiply it out, 2 plus 6 is 8, plus 3 is 11, and you double it, that's 22R. That's great. So the volume of the prism is 6, stuff that is jutting out of the wall is 22R. We are on our way to calculate the entire thing. Let's do some more. Let's see what's happening. Okay. Okay, so the next thing is that there are certain cylindrical volumes. For example, let me draw it using this orange. You have a cylindrical volume like this. A cylindrical volume like this. Maybe you can see this. This is a cylinder, because obviously it will be like one unit from this point will be all of these points. So same thing will be happening here, here, all of them, right? So it's a cylinder. It's definitely a cylinder, but it's like 1/4 of a cylinder. It's 1/4 of a cylinder, right? Because you can see, I mean, this is 1/4, and then you can do this 1/4, you can do this 1/4, and you can do this 1/4. So total the entire thing is there, but all the other portions are already included in the stuff that is either jutting out or the prism itself. So the extra stuff, that is 1/4 of a cylinder. So that's great. So let's calculate that. So the volume of a cylinder is, okay, so what is the radius of the cylinder? Well, the radius is r. The radius is r. So the volume of a cylinder is pi r square times the height, which is 2, right? But we would also have to make sure that it's 1/4. So it's times 1/4. Now one of them is on this opposite corner, like here, right? The same thing. It's on the other side, so we can't see it. So twice of that. And similarly, one of them is at this corner, one of them is at this corner. So there are like four corners. There are like four corners where this height 2 cylinder, quarter of height 2 cylinder is standing. So really, so these are all 1/4 pieces. So I can just remove the 1/4 and we have the entire cylinder now. Did you see how we got the entire cylinder, right? We got 1/4 here, sorry. We got 1/4 here, we got 1/4 here, 1/4 here, and 1/4 here. So total the entire cylinder, we have got the entire cylinder. Okay. So similarly, just as it happened with the height 2, the same thing will happen for the height 3. Well, this cylinder would be like this, like this. So this is also a quarter of a cylinder. So now this is 3 times pi r square. We will have 4 of them again. Each is a quarter. So a quarter of a cylinder. So total we have the entire cylinder. Same thing will happen with the 1. So you can just draw it using the green one, maybe like this. So again we have 4 of them. So 1 times pi r square, 1 times pi r square. So that's 1 is the height and pi r square is the area of the base of the cylinder. Okay. So total we have 6 pi r square. These are all the cylinders, right? Cylindrical areas. Okay. So we are almost done. We are almost done. The only part that is left out is the little spherical part that we have here at each of the corners. We have the little spherical part at each of the corners. And how many corners are there? Well, there are 1, 2, 3, 4, 5, 6, 7, and 8. We have spherical parts on each corner. Okay. So what part of a sphere? This is not the entire sphere. So what part of the sphere is this? So now here comes the challenge question. Challenge question. We have 8 pieces and each of them are portions portions of a sphere that you can see from this one edge that I have here. Okay. What is the total volume of these 8 pieces put together? That's my question. Okay. That will now give you the entire volume of the packaging and the prism, right? So that is 6 plus 22r plus 6 pi r square plus whatever you get here. That's the total volume. So I want you to think about this one. The last piece of the puzzle is up to you to solve. Put a comment in the chat section to tell your answer with a proper explanation, of course. Best answers in a given month are usually awarded with some book or something else, partial access to our programs, and so on. So I hope you can use that. If you are interested in outstanding programs in mathematics, physics, computer science, statistics, ISI entrances, Olympiads, or even research projects at school and college or university level, check the link in the description for more information. I hope you like the videos at chinta.com, and we always love to hear from you. So please stay subscribed and give us comments and ideas about other videos. Okay. All right. Take care. Bye. Stay well.